Okay, so today's topic then, we're talking about ratio, proportion, and rates of change. Some of you might have been to some of these PTI sessions about Enrich that Charlie and I have done before. And so we've gone through quite a few different topics and shared how Enrich in particular and rich tasks more generally can draw out certain ideas within particular topics. And so today is the turn of ratio, proportion, and rates of change. So we're going to be talking a lot this afternoon about how different representations can help students to develop a better understanding. Things like proportionality being represented as graphs through the origin, really about empowering students by giving them the tools that they need to solve ratio problems, because this is such an important part of real life mathematics. And so this is something that the better your ratio reasoning and multiplicative reasoning you are, the better your chances are going to be. And so we really want to provide an environment that students are going to thrive. So what we thought we would do is we thought we would actually start with a problem. And so hopefully you can all now see, this is one of the posters from the Enrich website for the problem, Mixing Lemonade. And I'm actually going to shut up for a short while, which I'm sure you'll all be very pleased about, and just give you the chance to read through the problem, have a go at solving it, and then if you can solve this super quickly, see if you can think of more than one way that you could solve the problem on the poster. Well, Charlie, why don't you talk us through one of your messages? A leader has shared a message in the chat. Look at the fraction of lemonade of the whole amount, or look at the ratio of lemonade to water in each glass. So yeah, that sounds like a couple of different methods to me. We can think about it as fractions or ratios. And so I guess the big question then becomes, what is it that we're looking at with those ratios? So Bimla's got a suggestion that you can work out the ratio as 1 to n and then use that to compare. So that often gets referred to as a unitary method. So I'm just actually going to annotate the screen a little bit for this. So I can write the first one as 60 to 200 and the second one as a ratio of 100 to 350. And the thing that makes it difficult to compare is that the two ratios, they're not out of the same amount at the moment. Neither of the numbers is equivalent. So if I could scale this to be 1 to something and this to be 1 to something, I could see straight away which is the most strong tasting. Was that either of your methods, the ones that we've just mentioned, Charlie, or did you come up with something different?
I was going to say you could leave your scribbling.
Okay. Well, let me put 60 to 200 back and 100 to 350 back. So what did you want to say about those ratios?
Well, I thought that let's imagine the first glass being poured out of a jug, and it's poured into 5 different glasses. So if I had all 5 glasses together, the 60 to 200 would be equivalent to having 300 lemon and 1000 water.
Mm-hmm.
In the case of the second glass, I'm not going to have 3 copies of it. I'm not going to have 5. I'm going to have just 3 identical glasses. So I will have 300 milliliters of lemon, and I will have 1050 of water. So the reason I've got 5 glasses of the first and 3 glasses of the second is that by doing that, I've got an identical amount of lemon in both. I've got 300 milliliters of lemon in both. And in the first one, I've got a little bit less water than in the second one. So the first mix will be slightly stronger.
Okay, so my observations from listening to you talk that through. First of all, you're imagining that you had 5 glasses instead of just 1 glass. I did a very bad diagram of that. But sometimes when students are first engaging with problems like this, drawing little diagrams to talk through their thinking can be a really good way for them to anchor their understanding. And it's also a really good way of picking up misconceptions, because if they're doing something in their diagrammatic thinking that won't work, you can draw attention to why it's not working. And so I've got my really bad picture, and then you've used that to multiply up to say how much of each there would be. So this idea of scaling the ratio. And so you wanted to have the same amount of lemon in each and see which one had the most water. So that would also work for Bimla's method posted in the chat, that if you worked it out as 1 to n, then you would be able to compare them, because you'd have 1 part lemon to how many parts water. It would not give you whole numbers in this case. So I think what's nice about your way of doing it, Charlie, is that you did everything as mental arithmetic. But if calculators are available, then we can start scaling things and writing things that way. So this is actually part of a bigger problem. This is the poster version of the problem. And one reason that we wanted to start off with the poster version of the problem is because, hang on, I need to get rid of the annotations, is because the poster version can make a really nice lesson starter, or just a homework, or something to introduce an idea that you can then talk about more. And going on from that, we can go to the main problem.
Before you do that, Alison,
here.
can we look at the fraction? Because we didn't talk about the fraction.
Okay. Yeah, of course.
Because again, that's quite nice, isn't it? If you think about what fraction of the total is lemon, so you've got 60.
So 60 out of 260.
Yes, and lemon. Of course, some students might be tempted to write 60 over 200. So 60 over 260 is the same as 6. I've made a mistake here in what I wrote. Okay.
It's 6 over 26, which is 3/13.
Yes.
And then this one is 100 over 350, which is 10 over 35, which is 2/7. Does that sound about right?
Yeah, I seem to have made mistakes. Yeah. But okay, and then you can get a calculator. And
yeah, I was going to say, I don't know 3/30. I know 2/7 is 0.28 something, but I don't know what 3/13 is. So luckily I've got my calculator here.
Yeah, but it's a good opportunity to discuss with students how would they work out whether 3/13 is bigger than 2/7 or not.
And then, of course, you've got the interpretation, because what does it mean for the fraction to be bigger or smaller in terms of what we're saying with regard to the with the strength of the lemonade?
And wait a minute, Alison.
Yes.
I think we've made the mistake that we were trying to avoid. It's not 100 over 350. It's 100 over 450.
450. So it's 2/9. Yes, that's better. Nobody noticed. Nobody noticed. Okay, now can I show them the main problem as it appears on the side?
I did have a third method, which was, instead of making the amount of lemons match, we can make the water match. So
okay, tell me about that.
Well, I think the lowest common multiple is 1,400 of 200 and 350 is 1,400. So
okay, so let me see if I can do this. So to get from 200 to 1,400, you've multiplied by 7.
I'm imagining 7 glasses.
So 7 times 60 is 420. I'm desperately trying to show that I can do arithmetic. 350 to get to 1400, you've doubled it and doubled it again, so you've times by 4. So I need to do 100 times 4, which is 400.
And
So
what's nice
this
about
one has less lemon, so this one has more lemon, so it's stronger. Yeah.
So what I like about these, my first method and my last method, are that once you've done this, it's very easy to tell which is the one with the stronger. The fractions was really awkward because I was left with these awkward fractions, and and I don't know whether 2/9 is bigger than whatever the other one was, the 37ths and so on. But I can also picture this, the idea of having a jug, and I don't just pour one glass, I pour 7 glasses of the first one, and then with the second jug, I pour 4 glasses. So I find it much easier to, and I think students find it easier to appreciate why you can be multiplying both sides of the ratio by the same amount.
Yeah, because one of the common misconceptions we see when people are working with ratio and with fractions as well is people trying to work additively rather than multiplicatively. And I think this idea of pouring lots of glasses reinforces what it is that you're why it is that you're multiplying, and why adding wouldn't work, because adding would be equivalent to putting some extra lemon in without putting extra water in, or vice versa. And it's quite clear that that's going to change the flavor of the lemonade.
Or even if you added the same amount of lemon and lemonade and water, again, that would change.
Yeah. So let me show then what the main problem on the site looks like that this poster was taking from. That's a lovely idea in the chat there, to actually try tasting some squash to see which is stronger by mixing it up differently. And I think with some classes I definitely wouldn't do it, but with some classes it might be a really nice demonstration to get their heads into that headspace of how is the taste affected by changing the ratios. So this is the main problem on the site, and it's got a little introductory problem there, but then when you scroll down, it's got this very cute little interactive where you can keep clicking and it will generate new questions. And then when you get a question that you like the look of, you can have a look at it and say, well, how would I work this out? So this has got 50 lemon and this has got 10 lemon. So this has got 5 times as much lemon as this. So if I multiplied up, if this was 50, this would be 250. But this has got 480 water. So the stronger one is going to be beaker B. And then when I click it, it tells me I got it right. And then I can generate a new answer, a new question, sorry. So this time, what have I got? If I times this one by 3 to get 30, I'm comparing the lemon here. No, I'll tell you what, I'll compare the water. I could double beaker B and then it would be 20 and 100 rather than 30 and 100. So beaker A has got more lemon in it, so it's going to taste stronger. And now I've got 2 in a row right. So the nice thing about this is if you're working in a classroom where everybody has got access to a laptop or an iPad, people can work individually on solving the problems. And if I generate a new answer and then let me deliberately get it wrong just to see what happens. So this one's got more water in, and so I'm going to say that it tastes stronger. Oh no, I got it right and it reset my score to 0. But you could set the challenge. Who can manage to get their score up to a score of 10? Who can get 10 in a row correct? And then that can be a way to show that you've really sort of gained the fluency in this activity. But not everybody's got access to iPads or tablets or computers in the classroom. And so I wanted to draw your attention on the left-hand side of the page. There's a section here that says Teachers Resources. And when I click on that, it has got some suggestions as to how to use this without the interactive. So you can get everybody working together on an example together off the board, but you can also use this worksheet, which just has some generated examples. So on the left column, you've got the lemon and water for beaker A. In the right column, you've got the lemon and water for beaker B. And you can just invite students to go down and have a go at these. So I think the challenge I'm going to set you is to have a look. I'm very quickly going to number the top few, because I think what's really nice to think about is whether you would use the same strategy for every question here. So let's call this A, B, C, D, E, F, G, H. And of the different strategies that we've looked at so far, so we've looked at, can you make the lemon the same? Can you make the water the same? Can you use a unitary method? Can you express it as a fraction? Can you express it as a decimal? Can anybody see a pair of questions here where they would solve one of them in one way, but they would choose a different method for another question? So I'm going to give you a little bit of time to have a look and to have a think about that. And then either share in chat, or if anybody wants to unmute and describe, you're very welcome to do so, and tell me two different sets of questions here that you might use two different methods to solve. Okay, would anybody like to share then the method that they might use for this top one just here? Because I think when we made this sheet, we deliberately made A one that you can almost do without a method at all. What's your thought process, Charlie, for A?
For A, I've got twice as much water as I have lemon in beaker A, but 3 times as much water in beaker B. So beaker A will be stronger.
So you're thinking within the beakers rather than across the beakers. Okay.
Yes.
I thought of it as there's the same amount of water in beakers A and B, but there's more water in B, so A would taste stronger. And yeah, I mean, you can do a unitary method. Somebody's just put in the chat, but you could do a unitary method with this, where actually you're not using 1 as your unit. You could use 100 as your unit, but because everything's divisible, you can also divide it down to 1. So I think A is quite an interesting one to talk about. Q Nazir, you've put in the chat that you would use dividing for set C and multiplying for set F. Would you like to tell us a little bit more about that?
Hi, can you hear me?
Yes.
Let me just go back to my chat. You're right. So for set C, where's it gone?
So for set C, we had 300 and 600, 200 and 400.
I think I've got the wrong set. I'm multiplying, I believe, for set B. So I'll double
okay, yep.
So I'll double it, the 100 to make 200.
Mm-hmm.
Whereas for F, one of them was divided the other way around, isn't it? Let me just have a look.
Oh yeah, I think I see what you're saying. So you can say what you're going to do to get between the beakers or within the beakers. So it's a bit like what Charlie was saying for the first one, that he noticed that the lemon was half the amount of the water, and so that feels like a dividing method. But then, yes, in some of them, it feels much more as if you're doing something multiplicative. Everybody's starting to put things in the chat now. Yes, it is closely related, Stanley, to the idea of concentration, and there is in fact a problem for Key Stage 4 somewhere on Enrich, which is all about using this for working out ratios and dilutions in chemistry. Joshua, we can use a picture method to divide. It doesn't have to be a circle. You could also use bar modeling for this and to show the proportions using different colors. Have we got anything else? Anyone else? I'm just conscious of time moving on and how many tabs I've got open of problems that I want to share. Does anyone else have anything else that they would like to say about mixing lemonade?
Yeah, when we were talking about the poster and we did the fractions, they were awkward. So actually, question that the top line is quite a nice one to introduce fractions, because 1/3 is lemon, 100 out of 300, and 1/4 in beaker B. And so we can see that 1/3 is, hopefully most students know that it's 0.3 recurring, whereas the quarter is 0.25. And so when you can compare those two fractions, you can see that, you know, if you can't picture that 1/3 is bigger than a quarter, you might be able to picture that 0.3 recurring is bigger than 0.25.
Yeah, I might draw something like that to help people to visualize it. Fun fact, there was an American burger restaurant that decided, as well as having a quarter pounder on the menu, they were actually going to change it so they had 1/3 of a pound burgers, and they were expecting everyone to flock to their restaurant because their burgers were bigger for the same price. And what actually happened was lots of people said, well, I'm not paying that for only 1/3 of a pound. I'm going to go over there where they have quarter pounders, because apparently people aren't very good at comparing fractions. So yeah, you can go away and look that one up later on. Let's have a look then at one more related problem that if you'd worked on mixing lemonade with a class, you might also want to share this. So this is one of Charlie's favorite problems, warm, snug, double glazing. The idea behind this problem is you're given, in fact, let me get the worksheet version up because I think it's a little bit easier to see it all. You're given the costs that some different panes, window panes would be, and you know that the price of the window is made up of the amount of glass but also the amount of frame, and the challenge is to work out what the pricing structure is and which one has been given the incorrect price. And so this is to do with the same sort of multiplicative and proportional reasoning, because you're thinking of how has the cost of the windows scaled up, and if you can find windows that relate and that you can compare in some way. So in the same way that we looked at places where there was the same amount of lemon but more water, we could look at places where there is the same area of glass but more frame, or the same amount of frame but more glass. And to help you with this, if you decide to use that method with your students, in the teacher's notes, there is somewhere, here we are. There is all of the areas and lengths worked out for you so that you can see them at a glance and start comparing them in the same way that we were comparing things in mixing lemonade. Right, I said that at past I was going to hand over to you to do the next bit, Charlie, and it is 16:31. So I'm going to stop sharing, and I'm looking forward to seeing what you're going to share with us. And I'm also going to remind you to unmute yourself.
Okay. So I'm going to share 3 short problems that we've published on Enrich. And just like we've done with Alison, it'd be interesting to see what different methods you come up with. Sorry, I'm going to cough. Okay, coughing's over. And I think the reason we're working on problems like this in this way is that we do want students to have that flexibility that when they've got a problem of this sort, they know that there are a variety of ways of solving this problem, and some ways are much easier, are more elegant, more efficient than others, but it's not always the same one. And so a classroom where students get given the problem, just like Alison gave us the initial problem from the poster, and people could talk about all the different methods, and then we can talk a little bit about which methods are easier to picture, to explain, to understand. Seems quite a good idea.
Yeah, and I think sometimes we feel a duty as maths teachers that we want to make sure that every student has access to one good method that will always work. And that's really important because we're trying to empower our students to know what they need to know. But I think it's also important that they don't get the idea of maths that there is only one method to solve things, because that's so not the case. So many problems, there are multiple ways to solve it, and getting them to appreciate that there are you've got lots of ways to choose from, I think is really empowering.
Alison, what can you see from my screen at present?
I can see the problem flapjack.
Oh, good. Okay, so we thought we'd start with this problem. Is the font big enough, Alison?
I can read it, but I mean, I have excellent eyes, so you could read it out for us.
A recipe for 8 flapjacks needs 2 ounces of butter, 3 ounces of sugar, 4 ounces of rolled oats. How many flapjacks can I make if I have 14 ounces of butter, 15 ounces of sugar, and 16 ounces of rolled oats? So like we've done before, if you'd like to post in the chat what you think the answer is and how you went about it, that would be great. Okay, that's great. We seem to have consensus here, and a lot of the solutions suggested are similar to the published solutions. So we normally, not with the short problems, but normally with other problems, when we first publish the problem, we call them live problems if we're inviting solutions, and then we publish student solutions. We haven't done that for the short problem, but the short problem solution for flapjack is very similar to what a lot of people are saying, looking at the limiting factor. So how many lots of 8 flapjacks could we make with 14 ounces of butter? Well, that's 7 times the 2 ounces of butter that you need for 8. 15 ounces of sugar is 5 times 3 ounces. So you could make 5 lots of 8 flapjacks. And 16 ounces of rolled oats is 4 times 4 ounces. And so the limiting factor are the oats. You could make more flapjacks if you had more oats, but so you'll have some butter and sugar left over, but it'll be 4 times 8 lots of flapjacks. And that's...
Yeah, I like the way that Lily described it as listing the maximum number of flapjacks that you could make for the constraints of each ingredient, and then noticing that it was the oats that, as you say, was the limiting factor.
Yeah, great. I think we can move on to fruit basket next. Can you see fruit basket on your screen, Alison?
Yeah.
Okay, now this got me thinking when we decided we were going to do this. So here we go. My fruit basket contains apples and oranges. The ratio of apples to oranges, so that these way of remembering that it's in alphabetical order, apples and oranges, in the basket is 3 to 8. But I get hungry, I eat one of the apples, I remove it from the basket, and what I'm left with is a ratio of apples to oranges of 1 to 3. And the question is, how many oranges are in the basket? So the number of oranges has never changed.
I think this one's harder. We might need to give people a little bit more thinking time for this one.
Yeah, I found it really hard the first time I thought about this. So yes, lots of thinking time available. So a few people have suggested 24 oranges. So I suppose one way of thinking about this might be to realize that if the ratio of the original basket is 3 to 8, then the number of oranges is a multiple of 8. And then when you remove one apple, the ratio is 1 to 3, but the number of oranges hasn't changed. So the number of oranges has got to be a multiple of 3. So then the number of oranges has got to be both a multiple of 8 and a multiple of 3. So 24 seems like a possibility. And then we can change our ratios, which are equivalent to 3 to 8, is 9 to 24. 1 to 3 is equivalent to 8 to 24. And if you start with 9 to 24, 9 apples and 24 oranges, and take away 1 apple, you do indeed end up with 8 apples and 24 oranges. So I'm not sure. Yeah, this is going to link up to, I think, what Alison's going to say with the interactivity. I don't think that's quite what I did the very first time. I think I didn't realize that. And I then did ratios which are equivalent to 3 to 8. With sort of 6 to 16 and 9.
That's what I've done just here, reminding myself of the answer to this because it's a long time since I looked at it. And I just wrote out 3 to 8, 6 to 16, 9 to 24, 12 to 32, 15 to 40. And then next to it, I've written 2 to 8, 5 to 16, 8 to 24, 11 to 32, 14 to 40. And then I've underlined 8 to 24. So
because that's got a ratio of 1 to 3.
Yeah. And it feels as if this might not be the most efficient way to do it, and that maybe if it had taken me longer to find the point of correspondence, then it wouldn't have been a good method. But it was the case of this is a method that I know will work. And of course, that's what a lot of students are going to reach for. But then the first time I solved it, after getting it, I then had the realization about what you just said about the having to be a multiple of both 8 and 3, that then gave me a new strategy that I could use. And I got quite upset that that I now had a strategy, but I didn't have any problems to work with it on. And that's why I went away and built a little interactive version that you just alluded to. Now, this is very rough and ready. I've not spent very long on this. If people like this and think it would be a useful classroom resource, I'll probably go away and spend a little bit longer on it. But all it does at the moment is chooses random numbers for the number of apples and oranges, and then generates all of the ratios. And then it's got a little checkbox so that you can type in what you think your answer is. And so sometimes you click on the reset button and it gives you something that's just trivial to solve. But sometimes it gives you more interesting ones. So it might be a nice idea to have a look at a couple of them, and I can go in and tweak some of the values to make more interesting problems if people think that would be useful.
So is the one on the screen now an interesting problem?
Well, see what people think. I think it's quite easy, but I've done loads of these because once I made the interactive, I generated things. Yeah, so this is on GeoGebra, Lily, and we will share the link with this along with all of the other links from resources. So I tell you what, I will put the link to this in the chat in case anyone wants to have a look for themselves rather than just at the one that Charlie's sharing.
Okay, so I agree. This possibly an easy one. So I'm going to reset. And I think it's easy because 4 to 5 is equivalent to 8 to 10. And if I can move from 9 to 10 to 8 to 10 by taking one apple.
So there's going to be 10 oranges. Why don't we just check what happens if you get it correct, though? Because I think I've built in so that it actually checked it. Yes, okay, good. This is correct.
I'm going to reset,
Mhm.
and I'm going to reset again until I get something that looks, because when I first did this, I was getting some which were a little trickier.
Yeah, as I say, it chooses the numbers completely at random, so you never know what you're going to get.
Okay, so perhaps I think we do want you to do a bit more work on this. Because so far they've been relatively straightforward. 5 to 7 is the same as 15 to 21. So I can, and you do have a conjecture about how to solve all these problems.
I think that the number of oranges, so you said that it had to be a multiple of the number of oranges in both of them. I think specifically it's the lowest common multiple. So we know that for this one, it would have to be either 21 or 42 or 63 and so on, because it has to be a multiple of both 21 and 7. But I think it's specifically got to be 21 because we've only taken one apple out. And I think that forces it to be specifically the lowest common multiple, which Joshua has actually said in the chat, the lowest common multiple will be useful here.
Okay.
So,
but okay, so maybe if you're going to do some more work on this, we need a second level where you take 2 apples or you take 3 apples, and then it'll be a slightly more interesting problem.
Tell you what, Charlie, if I can pay for somebody to get somebody to pay for my time to develop it, I will put in all the extra features you want. Just hit reset a couple more times and see if we can get one where, and again, that one looks more interesting.
Yes.
So, yeah, what's going on here? Well, we know it's got to be a multiple of 2 and 9.
So the lowest common multiple is 18.
If it was 18, then it would be, the top one would be 27 to 18. And then it goes to 26 to 18, which simplifies to 13 to 9.
Yes.
So that's quite nice. So it does occasionally give interesting ones. I think what I need to do is I need to figure out what to do in the random number generation so that it doesn't always give something. It's when you get prime numbers floating around, and I need to think of a way to condition on things being co-prime. But it's probably not a useful use of everybody else's time to listen to me speculating about how to write an interactivity. So maybe we should move on to the other problem that you were going to share.
Okay, so we've got one about printer ink. Do we have time for that, or do you want to go?
Yeah, you've got time. Yeah, you've got time.
Okay. So here's another opportunity to work on a problem which perhaps gets tackled in a variety of ways. And I suppose Alison and I are very keen to create a culture in classrooms where students leave feeling that there isn't just one way in which they are solving problems. That I know when my son was wanting some help with his homework, he wanted me to help him do it exactly the same way as his teacher had taught him. And the message he was getting from his teacher, which might not have been the message intended by his teacher, but the message he was bringing home was, this is the way to do it, and this is the way I need to do it. Okay, anyway, here's the problem. A small ink cartridge has enough ink to print 600 pages. 3 small ink cartridges can print as many pages as 2 medium cartridges. And 3 medium cartridges can print as many pages as 2 large cartridges. How many pages can be printed using a large cartridge?
Yes, I suspect Joshua's forgotten the last step and has actually worked out how many pages can be printed with 2 large cartridges. But I'm very interested with what Alida has to say about doing this visually.
Explain what I've done.
Is that all right, Charlie? I'm taking over your
Absolutely.
bit. You're in charge at the moment.
No, because you're looking at the chat. Keep going.
Yeah, Alida, do you want to tell me a little bit about what you mean by a visual method for this?
Yeah, I was thinking about bar modelling, but then I sort of changed it a bit. So I drew a rectangle to represent 600, so a small cartridge.
Mm-hmm.
I then drew another 2 underneath it, so I had 3 of those.
Mm-hmm.
And then I cut it in half so that I had a medium. And then I did another 2 copies of what I had next to it. So I had 3 mediums, and then I cut that in half to get 1 large.
Ah, yeah, I think I see what you're describing. So you drew something to represent the small, and then
Yes.
you're working through the multiplicative relationship between small and large by
Yeah.
thinking about your cutting and reassembling the rectangles to
And I think
represent it.
then that would be accessible to, well, those visual learners who can't always handle what to do with multiplying and dividing because they've got a picture to follow.
Yeah, I found this really interesting, you know, as a secondary specialist, as more and more bar modeling is going on in primary, and those kids are now coming up into secondary, and seeing just how powerful some of those visual strategies can be, because as you say, it enables them to visually see the unknowns that are being represented, and it can be a really good way of sort of starting people off towards the kind of thinking we want them to do algebraically, because the picture that they're representing then can become an unknown. You know, you can say, well, we don't have to draw a picture for it, we can represent it with a letter instead. So I think Charlie's going to draw for us.
Yes, I had something similar. So is that large enough? Can you see?
Yeah, we can see that.
I can bring this down. So 3 small cartridges was equivalent to 2 medium cartridges. And I wanted, and then 3 medium was going to be the same as 2 large. And I didn't have 3 medium there, so I added some more small ones, and that gave me another 2 mediums. And then eventually I was able to have 6 mediums. And for every 3 mediums, I would get 1 large. Have I got this right?
Yeah, that's looking right. Yeah. And so from your diagram, you can see that 2, 4, 6, 8, 9 smalls is the same as 4 larges.
Yes. And each small was 600 pages. So 9 times 6 is 5,400 pages. 4 large would be 5,400 pages. And then I'll have to divide 5,400 by 4 to get my 1,350 pages. So having diagrams is incredibly useful. And I think what I like about this problem and also the lemonade problem, well, and the double glazing problem, is that I've got ways of thinking about this, and it might be pouring more glasses. I mean, we didn't really talk about how the original poster problem, you could be thinking about, well, what if I just take a sip, kind of, or a thimble spoon, or a teaspoon? So we had something like, I don't know, 100 and 350. Well, they're all multiples of 50. So that was equivalent to 2 lemon and whatever it is, 7 water, and reducing it rather than increasing. Okay, I think I'll stop sharing now and let you introduce the next 3 short problems.
Okay, so yeah, we've got we wanted to talk about short problems mainly because I think not everybody knows that NRICH has got this massive back catalogue of short problems. So originally there was a short problem every week, and this this went on for quite a long time, that there was a new short problem on NRICH every week. Lots of them taken from UKMT challenge questions that were adapted, some of them from other sources. And NRICH no longer publish a weekly problem, but all of the ones that have ever been used, we went through a few years ago and mapped them to the curriculum, just as all of the other problems on NRICH are mapped to the curriculum. And the idea is that if you want something to fill a short amount of lesson time, rather than a full NRICH task, which could actually take multiple lessons to get all the way through, but if you just want a short bit of problem solving on a topic, then you can look them up. And so I'm going to share some more of the ratio, proportion and rates of change problems, but specifically on the subject of speed, distance, time, because when we're teaching ratio and proportion and rates of change, one of the most relatable bits of proportional reasoning is this idea of speed, distance and time. They do it in maths, they also do it in physics, and eventually they're going to need to know it in real life, because the number of times I'm going somewhere and I need to work out roughly how long it's going to take me, and Google Maps will tell you the estimated length of time of a journey. Oh no, I said the word Google and now my phone's woken up. Google Maps will tell you how long something's going to take, but sometimes it's good to be able to think to yourself, is it really worth overtaking this tractor? How much time is it going to make? How much difference is it going to make to the time that I got there? So this proportional reasoning with speed feels really important. So I wanted to share this problem. Don't be late. So Mary's driving to the airport. She goes at 45 miles an hour for the first 2 hours, and then at 70 miles an hour for the remainder of her journey. And I fully understand what's going on here, because I've been on that bit of the M6 as well. And so the average speed for the whole journey is 60 miles an hour, and you're asked to work out how long her journey took altogether. And so again, I'm going to give you a little bit of time to think about this, and then I'm going to talk through some of the different methods that you might use for this. So do drop anything in the chat that occurs to you while you think about this one. So hopefully you've had a bit of time to think a little bit about this one. I think a really common way of solving this is to start introducing some algebra to it, and to say, well, if she's gone at 45 miles an hour for the first 2 hours, that's 90 miles altogether. And then for some length of time, which I'm going to call t, she goes at 70. So it's going to be 70 times the number of hours, which I'm calling t. That's going to be her total journey. But that's got to be the same as if she did the whole journey at 60 miles an hour, which is just 60 multiplied by t plus 2, because it's the unknown number of hours and then the extra 2 hours she did at the start. And so I can solve that and get a value for t. And so that's the sort of instinct that I think a lot of maths teachers have to solve it. I don't think that's how many 14-year-olds might think to solve it. So I think a student might say that they go 45 miles and then 45 miles. So hour 1, hour 2, hour 3, and so on is going to be 45 and then 90, and then adding on a 70. So that's 90 and 70 is 160. And then adding on another 70 is 230. So this sort of trial and improvement kind of strategy that we've seen before. And then perhaps they'll spot that after 5 hours, 300 divided by 5 is 60. So I would be going 60, 120, 180, 240, 300 if I'd gone at a constant speed of 60 throughout. And so I can see that 5 hours is the point where they match. Another way that you could encourage students to think about this, I'm just going to pop over to GeoGebra for a moment, because I can use some graphical methods to think about this and say, well, if I'm going at 45 miles an hour initially, I can plot the graph y equals 45 x, and then I'm going to need to do some zooming on the axis here. So yeah, here you can see that after 1 hour I've gone 45 miles, 2 hours I've gone 90 miles, and so on. I'm going to plot that 2 hour point there, which is I've gone 2 hours for 90 miles. And so then at this point, the gradient's changing because she's going faster. So I want the line that passes through that point, but has a gradient of 70 instead of 45, because she's now going at 70 miles an hour. So I also want the graph y equals 70x, and then it's going to be minus, how do I get from 90 to 140? It's 50, isn't it? So I need to move it down like that. So this then shows the where she's travelled to after that. And we're saying that we want to find the point on that line, which is the same as if she'd gone at 60 miles an hour from the start, which is the line y equals 60x. And if I find where the lines intersect, which I can do in GeoGebra like this, then the point B just there is after 5 hours when she's gone 300 miles. So being able to show things like this can give a different representation. And I wouldn't use this with all students, but I would want students who were thinking of going on to do A-level maths to see this sort of representation, because familiarity with firstly with speed, distance and time graphs generally, but secondly with using graphical methods as a way of solving problems. The number of times when I'm working with A-level students that I end up saying, is there a picture you could draw that would make it easy? And some of them sort of think algebra is king and drawing a diagram is cheating somehow. And so getting across this idea that you're allowed to draw diagrams, you're allowed to draw graphs.
Can I say something about the algebra, Alison?
Mm-hmm.
Because the algebraic method was very, very neat.
Mm.
And sometimes I think teachers are resistant to show this because they possibly expect students to fully understand it and that maybe they're not ready. Whereas I think our attitude has been that you just show them that, oh, some people do this algebraically and this is what they do, and then move on. In much this, and that if students get exposed to this often enough, they start wondering, well, I want to know a bit more about this algebra. I can see that it's very, very efficient. You've got a very simple equation, and you could tell that what t was very, very quickly.
Hmm.
So I think without wanting to say, you've got to do this, to be able to demonstrate it seems very valuable.
Yeah. That seems like a really good excuse to jump and talk about temperature for a bit. I might come back and look at the other two short problems if there's time, but I very much want to talk about the problem temperature. So we might come back to Leggett and Late for Work. If we don't, we have included them in the list of resources that we're going to share with you. So if we don't get a chance to look at them before we finish at 5:30, then definitely go back and have an explore of them. But yeah, so this is again an old favorite on NRICH, the problem temperature, and it's based around this question in bold just here. Is there a temperature at which Celsius and Fahrenheit readings are the same? And if you happen to know a way of converting between Celsius and Fahrenheit, then you might have slightly different methods available to you for solving it. But if you don't know, the only information that you actually need to solve this problem is given here, that you know that there's scales that go up linearly, and the freezing point of water is 0 Celsius, which is the same as 32 Fahrenheit. The boiling point of water is 100 Celsius, which is 212 Fahrenheit. So again, I'm going to give everyone just a little bit of time to think about how you might solve this, and then we're going to share some of the ways that this has been solved. So please continue to share ideas in the chat as to how you think you might tackle this problem or how your students might tackle it. I think one nice way to get into this problem, if you sort of if you've never seen anything like this before, is to start tabulating some of what you're going. So if I have a degrees Celsius and degrees Fahrenheit, I know that 0 on this scale is the same as 32 on this scale, and 100 on this scale is the same as 212 on this scale. So I might ask students, well, if I went halfway between, if I went to 50 Celsius, how could I work out what I've done on the Fahrenheit scale? And hopefully they would use a little bit of proportional reasoning and say that they would expect it to be halfway between 32 and 212. And they might say that to get from 32 to 212, I have to add 180. So to get halfway between, I would have to add 90. And so 32 plus 90 is 122, I want to say. Does that sound plausible? Charlie's nodding. Good. And then I might say, well, okay, what if I wanted to go up by 10 degrees? And well, 100 degrees was 180, so 10 degrees must be going up in 18s, and so 32 plus 18 is 50. So I've worked out that 10 Celsius is 50 Fahrenheit, 50 Celsius is 122 Fahrenheit, 100 Celsius is 212 Fahrenheit. And then I can start thinking about the bigger question of, is there a temperature at which Celsius and Fahrenheit readings are the same? And it's really tempting for students to say, well, no, I don't think there is going to be, because this is going up by 10, this is going up by 18, and so the Fahrenheit is going to keep galloping away and the Celsius is never going to catch up. And then you can have this wonderful moment of realization that because we've got the context of temperature, and it feels very appropriate for this time of year, because I'm aware of the fact that temperatures are going to start going below 0 in not too many more weeks' time, and I can watch my fuel bill going up. But we can have negative numbers as well as positive ones. So then you can start saying, well, if I counted down in 10s here and I counted down in 18s here, can I start to home in on the time, on the temperature where they're both the same? But as well as being able to do things like this, sort of just using numbers, we could use algebraic methods. We could find the way of representing Fahrenheit in terms of Celsius or vice versa, which is part of the work that we need to do on formulae and being able to substitute into formulae. And I'm going to pop open GeoGebra again, because I feel as if I've not used it enough yet today. I'm going to delete everything that we already had on here, and I'm going to show one way that we could, come on, delete. One way that we could use GeoGebra to solve this problem. Why aren't you showing me? There we are, delete. Okay, so I'm going to plot the points. I'm going to have Celsius on my x-axis and Fahrenheit on my y-axis. So I know that when Celsius is 0, Fahrenheit is 32. And I know that when Celsius is 100, Fahrenheit is 212. So I can represent, let's do, I want to get 100 showing. There we are. Let's do a straight line through those 2 points. And so GeoGebra has given me the equation minus 9x plus 5y equals 160. I should be able to change that so that it is in the form y equals mx plus c, but I can't remember how to do that in WebGeoGebra, which is annoying. Settings. Okay, I'm not going to look for a GeoGebra setting now while you're all patiently hanging on to my every word, but you can set this up so that instead of having it in ax plus by equals c form, you can have it as y equals mx plus c. And then I could just go down the line and look for a point where the where they match up, or I could save myself some time by drawing the line where the y coordinate and the x coordinates are the same, and just use the intersection point like this. And then at the intersection point, you can see that the Fahrenheit is 40 and the negative 40, and the Celsius is negative 40. So that's going to be the solution of the problem. And so if we go back to the problem temperature and look at the student solutions, you'll see all of the things that we've just discussed are things that students submitted when this problem was published on the site. So some students noticed that if you went down by 9 on the Fahrenheit, you went down by 5 on the Celsius, which is equivalent to our 18 and 10. Here's the formula for getting from Celsius to Fahrenheit, and that you can then rearrange to have it the other way around. And then you can find various different things by using these sort of trial and improvement, or these what do you call it, algebraic strategies. But if I keep going here, you've got a graphical approach that looks very like the one that I just did in GeoGebra, and then down at the bottom you've got the different ways of working it out algebraically. So what would be quite nice to do in the classroom is to share this problem with students, but then share all of the different solutions. So not just the way that people in the class come up with to do it, but also the student solutions online. And this is something that lots of teachers find very valuable about problems on Enrich, that these student solutions are there and are available, so that even if nobody in the room happens to come up with a particularly clever way of solving a problem, rather than you as a teacher saying, oh, this is how I did it, which sometimes kids can be like, yeah, but I would have never thought of that. You can show them these are genuine student solutions that really clever students from a different school came up with. And it just sort of brings it within grasp a little bit. It makes it seem like something that somebody like me might have been able to do. There is one more thing to mention on the subject of temperature, which is a link that I've made Charlie put into the notes from today, because one thing that we've sort of hinted about in what we've talked about is that ratio and proportion and rates of change can often have lots of misconceptions built in. We've talked about the misconceptions to do with adding things when we're working with ratio rather than being in that multiplicative mindset. There's some massive misconceptions when we're working with temperature, and you can hear this sometimes when people who aren't from a maths or science background are talking about temperature, and they might say things like, the temperature is going to double, or the temperature is going to halve, which doesn't make sense unless you're using a scale like the Kelvin scale of temperature, which has an absolute 0. So halving and doubling are multiplicative relationships for things where you can do the proportional reasoning using 0 as your baseline. And that doesn't apply to temperature. And you can easily see this by saying, if the temperature was 0 Celsius and I said that it was going to double, then it would be 0 Celsius again tomorrow. But if I measured it in Fahrenheit, it's 32 Celsius today. Does that mean it's going to be 64? It's 32 Fahrenheit today. Is it going to be 64 Fahrenheit tomorrow? So it's interesting to share that with students. For you, though, I've put in a link to something that Steve Mould has on his YouTube channel. He's does some very good science communication and also comedy, and it's from one of the Festival of the Spoken Nerd gigs that he did, where he describes some of the problems when you come across people who don't have the same conceptual understanding of temperature that you do. And it's a fairly short watch. It's under 10 minutes, and I find it quite funny. So that's included in the notes that we're going to share with you. I said I would go back and show the other 2 short problems if there was time. What I wanted to say about Leggett, we're not going to go through this whole problem, but the idea is that you've got 2 people training for a race, but one of them is quite a lot better runner than the other, and working out if you did a staggered start so that one of them, so they both start on the same gun, but one of them starts ahead of the other, or the other one starts behind the slower person, what distance should you make it? And I think what's interesting about this and why it's a good problem to share with students is because of the way that you're that you're scaling, because you're using proportionality, the amount in front, if you let the slower person have a head start, I think she has to be 20 meters in front. But if she starts at the normal 100-meter line and you make the other one start behind her, she has to go 25 meters back. So you've got this asymmetry that I think the first time you see something like this, it just provokes well, that's a little bit strange. I would expect it to be the same. And it's the same concept as when you have percentage discounts and percentage increases, and working out, I always talk to my students about what the denominator is and making sure that when you're doing any of this reasoning and scaling, you know what the denominator is, because if you know the amount after the discount has been put on and you want to get back to where you are, then you're not doing it out of 100, you're doing it out of whatever, and then scaling back up. I don't think that made any sense at all, but maybe it did.
Well, but that links up to Leggett, for example, Alison.
Mm-hmm.
Why should the distances be different? Well, if the slower person starts in front and the faster person does 100 meters, that race will take less time than the race when the faster person has to run more than 100 meters. And therefore it makes sense that the difference between the starting positions is longer when the race is longer.
Yeah. I'm going to say one more thing about counterintuitive things with when you're working with speed, distance and time. We won't go through this problem because, as you'll be able to see, it is a challenge level 3-star, which means it's among the hardest problems that we've got for the age 14 to 16 age range. So it is definitely one to go and think about, but it's effectively about averaging average speeds. And I have one thing to say to you on the subject of averaging average speeds, which is that you need to look up the concept of the harmonic mean. We don't really teach about the harmonic mean, except that it comes up implicitly in questions like this. But when we're doing the mean of things, you know, it's really tempting to say, this is 20 miles an hour, this is 30 miles an hour. So we need to do 20 plus 30 divided by 2. So 25 miles an hour to find the average speed. But that would be just using the normal arithmetic mean. What you actually need to use quite often for questions about average speed is something called the harmonic mean. And I don't remember coming across this for quite a long time. And then it turns out that it's quite interesting. It's got some quite interesting properties. So that's something to go away and have a look at for its applicability to speed, distance and time problems. There's a nice bit on the Wikipedia page for different types of average about this. That felt very rushed. Have I said everything that I intended to say, Charlie? And could you unmute yourself before you talk?
Yes, I think so. I'm not sure we've on the chat, I'm putting a link to a page on the site that we've published for you. Let me share my screen and then I can share it with you.
Yeah, so that link that Charlie's just put in the chat, that's got links to every resource that we've looked at today, along with some other links to further reading that you might find useful. And we'll be sending this out to you. Well, we'll get somebody, probably Eden, to send this out to you after today as well, so that you've got this link if you don't grab it now, together with our contact details. So Charlie's contact details are all available on the NRICH website. I'm pretty easily findable, but I will make sure a link to the contact form on my website comes out to you as well, in case you want to talk to me about particularly any of the GeoGebra bits that I've done today. But yeah, I hope we've given you some food for thought on the topics of ratio, proportion and rates of change, and that some of these problems look like something that you might like to go away and have a go at. But I did promise I would hand back to Eden by 2 minutes before the end to do the final wrapping up. So I just want to say thank you everyone for all of your participation today.